Thank you very much. And it's a pleasure to be here at last. We tried to get this going almost 3 years ago, but it's taken a little time. And also things have moved on since then. Had I come in early 2020, then probably some of the things which I'm able to present today wouldn't have been possible because they were still work in progress. So that, as Julia said, the book is now as complete as it's going to be, so it's gone to the publishers, and we hope it will be out in May. There's a typo in the link here, so the link should have the .org as you said. But that's online, and we welcome issues. If anyone finds something that still needs to be corrected, we can still get it done in the proofs before the book gets frozen by the publisher. So that what I'm going to try to get through is to look at how coordinate reference systems are handled in the most typical approaches in free and open source software, which is the Proj library, the support for datum transformations in this, which have changed quite radically, and how these are then presented, implemented in R packages and Python modules. I'll also touch on something which I also mentioned on Tuesday, which is the S2 geometry library for handling topological predicates and operations on the surface of a sphere rather than on the real surface. Now, one could, and with reference to what Julia said, one could possibly not complain if people don't get the point of what coordinate reference systems are, if they see, well, it's just data. But one of the points which we try to make in the book is that spatial data are, yes, they're data, but there's a context to the data. And it's the context which makes a difference in terms of being able to register the data, so that diverging from the script, it's something you see in time series. So if you have time series, but you're not quite sure which time zone they're in, most sort of basic science would say, okay, time is time, but it's UTC. It's Greenwich Mean Time, it's UTC. If it's not UTC, it's not time. It has to have a reference frame. And it also has to have a reference frame by its complete definition, because things like leap seconds happen. So that saying that the difference between the 27th of February and the 2nd of March is always the same length. It depends whether you're on leap year or not. So that there are some details, picky, irritating details that happen also in time series. And coordinate reference systems are very much the same kind of thing, but in 2 dimensions. But become somewhat more complicated, as we'll see, because yesterday I was downtown and found the plaque marking the point where the decision to introduce regular time zones was promulgated and decided by the railroads in 1883. It's harder with time, but even so, the time zones which were applied within the US, they applied to the US. They didn't go over the Canadian border, I think. I don't know, maybe they did, but they certainly didn't go over the southern border. So that when you're trying to reach definitions which cross the borders of jurisdictions, then you need more, that more needs to be going on. Now, spatial data can occur in 2 or occasionally 3-dimensional space, reference to orthogonal axes, typically on the real surface, the real plane, or possibly in a volume, but where the axes extend to infinity. If you're on the sphere, the axes can't extend to infinity. They can only get round to the other side, and if you want to go to infinity, you've got to go some more laps round the globe. so that there are different structures involved here. So what are these coordinate reference systems? The principal distinction is between those which are ellipsoidal, so defined on the surface of the ellipsoid, or on the real plane. In Cartesian coordinates, then we might say that Z is taken always as unimportant, just got X and Y. However, with spherical coordinates, then we'd have a measure of longitude and a measure of latitude. And one complication, which I'll note now, but which we may get back to, is that the axis order may differ. Typically on the plane, you talk about X and Y, and X being a horizontal axis and Y being a vertical axis. Very often on the sphere, you put the latitude first, and different standards for definitions of coordinate reference systems also do this. With some geodeticists, they will typically put the latitude first, so that's the northing, and put the easting second, which is the other way around. So it's the axis order question also arises at this point, depending on which scientific domain you're coming from. Now, one of the difficulties which arises in relation to ellipsoidal or spherical data, if we're in a planar setting, then we can get a better grasp on what we mean by zero altitude. But this is also the place where the two representations cross each other, because is zero altitude on the surface of the ellipsoid as defined by the math, or is it related to mean sea level, which would be typically the way surveyors did it years ago? So they got some point of measurement, which was then accepted arbitrarily as being the zero mean sea level, and that other altitudes were measured above or below this. Now the ellipsoid generalizes so that it's smooth, whereas the geoid is bumpy, partly because of differences in gravitation. So that sometimes the geoid mean sea level is actually below the ellipsoid, and in other places it's above, depending on what's going on way down, so deep under the surface, and the density of the mantle, things like that. So there are a number of choices which may need to be taken. One book which Edsa and I have found very useful is I Live and Lot. Lot is also involved in quite a lot of the standards activity. So their book about how to represent coordinate reference systems and how to handle transformations between them is a good guide, because it's partly written by one of the people who's making the decisions on standards. Now, one of the things that one realizes fairly early on is that the shape of the Earth plays into this jurisdictional distinction, which I've already drawn. The jurisdictional distinction tends to mean, in terms of the ellipsoid, which is chosen by a particular national mapping, typically a national mapping agency, but in the US it could be a state mapping agency, would be the one which best fits the geoid in that place. And it may not fit the geoid very well in other places, but it's an easy way of approximating the geoid for the jurisdiction in question, so that the Ordnance Survey in the United Kingdom uses a particular representation of the ellipsoid, which works quite well for the datum which was chosen in 1936 in the UK. In other countries, it's similar. So there's an overlap there. The main distinction then would be between geographical coordinate reference systems, known by abbreviation as geog CRS. So they're on the ellipsoid, and projected proj CRS are on the plane. If you include a Z, then there would be in a volume. If you include a radius of the geoid in the ellipsoidal system, then they're related to that possibly arbitrary measure. It's difficult to say that there's a true distance to the center of the Earth because that's unobservable. So in order to approximate it, you have to make assumptions about the shape of the ellipsoid. So when in doubt, one can go to Eilif and Lot. Another question which arises, which I've already mentioned, is that in Euclidean spaces, so the real plane, you can go potentially on forever and ever. Usually, the representations which are chosen are numerically sensible, so that you don't get hundreds of millions of millimeters. So the numbers are kept to something sensible, which then don't overflow on a computer. As when quite a lot of this was done, one typically used single precision, not double precision, and computers were 32-bit at the best. So you wanted to have some number which was sensible. And if you think in terms of older devices and measuring equipment which you'd be using in the field, it didn't have that much numerical precision. So in the US, it might be in surveyors' feet. In India, it's also in Indian feet. In the UK, it's in meters, which was a brave decision taken at the time, and so on. So there will be a way of saying what's the basic unit that we're using. On the sphere, we're dealing in decimal degrees, and that's it. So that's on the other hand, they're bounded. So the definition of the coordinate reference system, which we drew from Lot 2015, is that a coordinate system is a set of rules applied to how coordinates are assigned to points. So that's meters, or so how you're going to measure them. A datum is a set of parameters that define the position of the origin. So this will be the prime meridian, the scale, and the orientation of a coordinate reference system. And usually you'd want a coordinate reference system to be north-south. Climate modelers and meteorologists quite often twist the grids of their representations, simply because they're trying to model outcomes for an area which has a diagonal bounding box. So that instead of having a big bounding box with lots of meaningless stuff here, then you rotate the bounding box so that the model outcomes are mostly for areas that you're interested in, and they can be quite a problem to handle. A geodetic datum is then related to the Earth itself. Coordinate systems and datums could be applied to any other planetary body. But a geodetic datum is usually applied to the Earth with a capital letter, and a coordinate reference system is then a coordinate system that is related to an object by a datum. For geodetic and vertical datums, the object will be the Earth. So this is the formal definition. Now, that's fine if we're just dealing with one data set. But if we're dealing with multiple data sets, some of which may have been registered in previous times, then we get to the challenge or difficulty of conversion or transformation. It shouldn't be hard. If there is no change in the datum, coordinate conversion is just a mathematical operation. And in principle, it will be lossless. Numerically, it's not completely lossless because all trigonometry involves is you're losing the least significant digit, maybe, or a couple of least significant digits. But in principle, everything stays the same because you're not transforming the datum. The other, the conversion operations are all just trigonometry. So that shouldn't be a problem. So say the underlying datum is some version of NAD 83, North American datum of 1983. There's Han, which is more precise, a more recent version of the same thing. Assuming that what we have are geographical coordinates, so a geographical CRS, and we want to move it to a projected, like a state plane CRS, but the datum is exactly the same in both cases, then all that we're doing is trigonometry. However, very often, as insight has increased, and I'll get to how it's increased in a bit, you may need to transform the data because the datum of the older data that one had are no longer the same. And this then involves coordinate transformation, datum transformation, because not only is one conducting possibly a conversion from geographical coordinates to projected coordinates, or from one projection of coordinates to another projection of coordinates, say from state plane to UTM. Just as an example, if datum transformation is involved, then the transformation will most likely not be lossless. It may be the case that the transformation involves introducing imprecision which is not of importance for the study being undertaken. But one still needs to be aware of the fact that so if you're dropping points down onto a satellite image or integrating a satellite image with other data, so maybe it doesn't matter. So maybe you're going to hit the same raster cell, maybe you're not. When we were thinking in the last century about satellite imagery, then having pixels which were as big as a block, so they're big. So it didn't matter so much, but now with 2 meter, if you can get hold of some of the military stuff, then it's at 25 centimeter. Then the level of precision has changed, and the kinds of things that we've been doing for. Everybody here would say, well, it's been forever, but we haven't had Google Maps and being told how to navigate on streets and stuff for very long, really. But they operate within just a couple of meters, especially if they're using augmented GPS or using a mixture of GPS and GLONASS. They're pretty precise, unless there are big buildings around, so you can't see the satellite. But this element of precision comes in. One of the other things which happens in the technical side of definitions is how to account for time. Datums are okay, but datums, the definitions only really work as they have a consume by date, which is concerned with the movement of tectonic plates. If you're in an area with a lot of earthquakes, then the assumptions which were being made in both in eastings and northings and the distance between the ellipsoid and the geoid, they vary. Because earthquakes can lead simply to vertical movement, which means that well, for our purposes, we think it's not much, but a meter or two makes a difference. So that earthquakes can happen. So there are sudden changes, which, again, if you're looking at something at the county scale or even at the census tract scale, it's not really making a great difference. But if you're doing detailed work, say in precision agriculture, then you need to have the datum definition, which is appropriate for the epoch of the data, so that the most extreme geodeticists that I've met maintain that each observation should have 4 components: the X, the easting, the northing, the altitude, and when it was observed. So for each point, on the boundary of each polygon, you should have four components, and integrating that into software has been quite hard. It's now done in the Proj library, so that the abstraction has 4 elements. The final one is a date time. It will usually be the number of minutes or the number of seconds since some beginning of an epoch, but the idea of an epoch is important. This also applies to where in the world you are, and how things have changed. So that one of the things which happens is the definition of terrestrial reference frames or terrestrial reference systems. So I come back to this a little bit. I'm not going to go back defining them. So one of the ways in which this is handled, say in Australia, is to anchor the local datum to tectonic plate, so that you don't have to change the local maps, but you know that the placing of the local maps in relation, say, to GPS changes over time, because the plate is heading off in a particular direction. If you're on Iceland, then you get the same kind of thing, that bits of Iceland are heading off in different directions, and although the local reference is keyed, it's registered. If you're trying to put that in relation to some other reference system, then it becomes for geodeticists great fun. They really enjoy this. Have these things changed recently? Well, not really, because surveying, when it was done, so we're at 1776, and we've got artillery, and what do you do mapping? What's the purpose of surveying and mapping, apart from property boundaries? Property boundaries and the cadastre have always been important, but they've almost always been anchored to a visible landmark, so that most cities would use the cathedral tower. But by the time we're getting to the late 18th century, then the main purpose of surveying is to align artillery so that it hits its target. So before that, artillery was more, it wasn't able to shoot as far, and you could just look along the barrel and say, well, it looks as though that will be okay. And if it's too short, then you raise the barrel a bit if it goes too far. So but they weren't surveying. But by the time you get to the 1770s, where did Napoleon go to school? It was an artillery school, and the same thing for the artillery officers in the British Army wasn't very up on math, so that being good at math and being able to position your artillery correctly was a big thing. So that in the United Kingdom, after the unpleasant experiences of meeting people who had math, they created the Ordnance Survey. Ordnance is artillery. The Ordnance Survey, it was to be able to provide surveying tools so that you could achieve your targets or hit your targets. Ships didn't need it, because at the point at which they could hit each other, they could see each other. They could probably see the colors of the eyes of the opposition, so it didn't matter. But the army and artillery, they were firing over longer distances. They needed surveying, and from there you get the development of mapping as something to do with command and control. Air balloons, hot air balloons could be used. You could use those, and by the time you get to all of this is military. First World War, oblique air photographs. So it was taking a passenger was a photographer up in a reconnaissance aircraft, so that instead of the pilot flying a single pilot aircraft and flying over to see whether they could see where the opposition was, then you would have a photographer who'd be taking pictures, which in the 1910s, these were plates. So it's heavy duty stuff, but aerial photography came in. So through the Second World War, a lot of the effort of air forces was relating what they'd been able to capture from air photographs. You needed what were known as ground control points, and in very many jurisdictions there weren't complete sets of topographic maps. So that, for instance, in Norway, there wasn't a complete set of topographic maps. That the first complete set of topographic maps for Norway was made by the occupiers. So because they couldn't handle a situation where the locals knew where stuff was, but it wasn't on a map anywhere. There were some sketch maps, a bit like the ones you probably have seen from Switzerland, with where there's a steep slope, then it's hashed in. And that kind of thing, but there were very few measurements. There were some surveys of done by people claiming, I've climbed the highest mountain, and then somebody else would say, my mountain's higher than yours, so that they'd be competing with each other to do the surveying and find out. So that finding out how high Everest was a real task, because you had to do it by hand. As you were establishing the baseline of a triangle, to triangulate in. In the Netherlands, the triangulation is based on the tower or the spire of the church in Amersfoort, because you could see it from a very long way away, so they could use it to establish the triangulation. And the mapping system used in the Netherlands is a triangulation based one. The European datum of 1950 differs from country to country, but is said to be anchored to one corner of the tower of the cathedral in Munich. Don't ask me why, but presumably it was a good place to put it. One of the things which has influenced mapping is our military alliances, so that when the Warsaw Pact was established, then the Warsaw Pact had to have one standard for projected CRS, and the same with NATO. NATO used UTM because it then, so that Norway got, during the 1960s, Norway got a set of maps which were essentially made for NATO because they were in UTM, rather than in the local one, which I'll get to in a moment. So the way things then rolled through were, so up to the 1960s, everything was from the surface of the Earth or air photographs. Once you go beyond that, you're starting to get military applications in space, both Earth observation and the ability to do geometry from space, so that establishing a reasonable estimate of the shape of the globe is, if you're going to try and chuck ballistic missiles across a globe, you have to know what shape it is. So that the initial observations were classified, so there was military secrets. In India, many maps are still military secrets. It's not as though the Chinese don't have satellites, but India still has a rule that you can't have access. When I was working in Poland in the 1970s, you could get sort of maps of the whole country or a map of a city, but it wasn't very precise. But anything more precise was kept in a safe and had to be checked out. You had to sign for it. And I was allowed to look at the maps, but they said, well, we shouldn't really be showing them to a foreigner. They have to be somebody from the Warsaw Pact, not someone from NATO. And they were dreadful maps. They were just black and white, and they were 1 to 150,000. So no precision at all, essentially, and that was the best you got. Anything else would have been held by the military. So that so when you see here in the text, it was the U.S. Department of Defense which was funding all of the measurements which were being used, particularly in NATO or in the West. The first GNSS, GPS, but it wasn't GPS yet, came in the 1970s. Surface measurement was used. The LORAN system was used a lot by navies and the Air Force, but it was based on having radio transmitters, terrestrial radio transmitters. Then you could measure the distance from them. And it has been suggested that they should be reintroduced in case GPS is taken out. Because if the GPS systems go away, then quite a lot of navigation goes away, and you have to go back to having paper maps and stuff. So that around about the early 1980s, there was this WGS-84, which is where we tend to think that everything is WGS-84, but it was a committee decision. It was the next iteration of the World Geodetic System. And it provided a view both of a datum which worked for the whole world and an ellipsoid definition for the whole world. From 1989, the then end of the Cold War, things really started rolling along, and it started being important how to represent things. Before that, then you took the representation you could get, so that anybody working in a particular place, say in a US state, would use the state plane for that state, almost certainly defined in NAD 27, which is based on the Clark 1866 ellipsoid. So you use an 1866 ellipsoid and the NAD 27 datum. And that was how most of the state plane maps were introduced. And you then start to see why actually you could say that changes have been happening recently. But what's been happening is that software, which was largely defined and written for a world without high precision measurement, is trying to adapt itself to high precision measurement, which to us seems completely it would be unusual if it wasn't precise. If you got out your Google Maps and you want your present location, if it said, okay, I can give you this, but you're within plus or minus 100 meters in each direction of this, you say, wow, this is hopeless. But until Clinton signed the degradation of, or the end of degradation of accuracy for non-military purposes in 2000, which is only 23 years ago, that was the way GPS worked. So that for civilian purposes, you could be here or you could be on the other side you'd be somewhere up by the Roby House, or a little bit closer, but you'd be somewhere there. So you'd know where you were in the city vaguely, but you wouldn't be able to have much more control. And the software which was written prior to 2000 did that, so that that's why changes have been occurring, and they've been taking quite a long time to occur because people have been putting it off. And do we really want to make changes to how we handle coordinate reference systems? Can't we just say that it's in geographical coordinates and be done with it? Well, you can, but if you're then trying to integrate data, this becomes somewhat problematic. So this is then using the corrected Boston data set, the one which Gillian Pace provided, with what they gave as longitude and latitude. it's not a great fit. But that's something I did ask Kelly Pace why the points don't match the map. He said, well, at the time we didn't have a map. This is 1995, 1996. And the students nowadays would have gone out to each tract and measured it if they hadn't thought simply of downloading it. But it's off. It's actually, you can make a transformation. You can shift it so that the UTM version was after, I think, the version which is in the Geodar data directory is from the UTM-19, which I attempted, as I found some known points and then did just a mathematical transformation from these points to those. But then, anyway, so that's. Mm-hmm. So these are the, and this has only been possible since we've had web maps that we can dump the data on. Before you draw a map and it would look plausible and you wouldn't be concerned with the context and drawing out things. In fact, probably everything should be moved somewhat to the, I don't think it's just a north shift. But you can see here we're in downtown Boston and there are almost none of the observations. So it's probably north and moving a little bit east or perhaps rotating a bit. But I tried to do something like that when I saw that after the paper came out in 1996. So that, yeah.
So you're saying that throwing the dots just in map view or whatever, right?
Yeah, this is in map view.
Is a legit check whether something is off? Because I'm doing it quite often. I was not. Since you do it, it seems like it's that's good approach.
Yeah, but MapView's been around since 2015. Before that, we made it into a KML file, keyhole markup, and dumped them on Google Earth. But Google Earth's only been around since 2006, 7, and then writing a KML file wasn't so easy. So this facility to check whether things appear to be where they should be has only been around. It wasn't around until at least 10 years after the Gillian-Pace paper came out. I think that Kelly's version was that they had some students doing what they thought was digitizing, but it could well be that the students were digitizing from a state plane map. They didn't know what they were digitizing from, and it was never recorded. But at the time it didn't matter, and actually the relative position of the tracts doesn't change much. Mm-hmm. So that's sort of an example of what can happen when things. Then we have a shapefile soon to be turned into a Geopackage file for the Boston tracts. These were, I was approached by Anthony Unwin and Bill Venables. Anthony Unwin's from graphical data analysis, to say that they use the Boston data set a lot, but they wanted to know whether it was possible to find the tract boundaries. And this was in 2011, so I was in Columbus, Ohio at the Spatial Statistics conference, and there, because we were on campus, then we could get into some data sources. What's it called? ICPRS. If that it's like some combination of those.
ICPSR, yeah.
Where there was a table showing which tracts from the 70 and 80 and 90, so that you could, if you got the 90 boundaries, which were great to download from the census, then you could backtrack and aggregate and chunk and mix and chunk the tracts so that you could identify the tracts. The data set had the tracts numbers, so you're good to go there. And you could download and move to the correct. So, but I said, okay, so that if we're dealing with 1990 boundaries, so that probably the census was at that stage using North American datum of 1983. Well, why not? 1983 is after 1990. So the data set as we provide it in the SP data package has NAD 27, which you can see here, which I'll demonstrate shortly that the 1990 census boundaries appear to be in NAD 27, not in NAD 83, even though they were produced after NAD 83 was available. And probably for backwards compatibility. So they wanted not to mess up work which people had done before. But if you go to NAD 83, and perhaps I should also explain the presentation style of using a not slides but a continuous document, which is Edsa and I were told by Angela Lee in Toulouse in 2019 is that nobody uses slides anymore, and you have to do it this way. So since then we've been doing it this way. She was very definite, and I think she's right, because then you can move more easily, so up and down the slides. But if we then go into, and it's only when you start putting the actual tract boundaries in place that you can see where tracts were missed out of the data because there were no housing values there. Because you needed to have something which could be identified as a house rather than a rental. And there were some parts of downtown Boston where there were no houses, but there were rentals, and they're not represented here. So this map is also showing the whether it's censored or not. But if we go in a little closer, this is then assuming that we're using NAD 83. We're missing the center lines of streets, so we're still off. So my first iteration was to send Bill Venables and Anthony Unwin, say it must be 1983 because it's that. And then they got back to me and says that it's not on the center lines of the street. So there's something is not right. So then we went for NAD 27, and NAD 27 appeared to be, and those of you who were watching this by having accessed the slides themselves, you can see that the track boundaries are very coarse, so they could have been much better resolution, but they're now much closer to the street lines. So we went with NAD 20. We said it's probably NAD 27. If anybody needs to look for references on the International Terrestrial Reference System, then the Wikipedia page is fairly up to date. Now, one thing which I think I'll be mentioning later on, but which I'll also mention now, is that when shapefiles were developed, and as I mentioned on Tuesday, the definition of vector object in the SP package was based largely on a shapefile understanding of the world, of how geometry should be represented. The initial shapefile definition said that the PRJ file, the projection file, was optional. And in today's world, that's not optional. You can't have an unknown coordinate reference system. One of the things which this then leads to is that the Geopackage says that if you don't declare a coordinate reference system, it assumes that you're using geographical coordinates in the WGS 84 datum. If you don't, it says if you don't give a CRS definition, that's what you get. But it doesn't do a rationality check to see that those numbers of degrees make any sense. Mm-hmm. So that you could have a northing which was and choose something nice, like how far would you have to get from the equator in meters? Well, if you're just saying kilometers, 6,000 kilometers from the equator, so 6 million. So you can have 6 million degrees of latitude. And as I initially did try it out, and I thought, well, they must have a sanity check somewhere. But no, if you haven't declared it, you get geographical coordinates, which then led us to scramble to put in a. This will be in the next version of SF, which will be coming out shortly. Where if you try to write a geopackage and haven't given a coordinate reference system, then we impose an unknown coordinate reference system which looks like this, but it's planar. That's the way we've been doing it since forever, that if you don't state what the coordinate reference system is, it's planar. We don't assume geographical coordinates. There are some other complications here as things have moved through. The GeoJSON, the early GeoJSON standard said that it's up to you to give a spatial reference ID, like an EPSG number. More recently, it's been changed to say that there's only one valid representation, which is WGS 84 and geographical coordinates. That's the only valid GeoJSON, but you find a lot of people using the previous understanding of GeoJSON using projected coordinates. What do you do if you're stuck? You've got contemporary data, but you also need to integrate older data. One of the best sources is the Grids and Datums column by Cliff Mounier. He's now long retired, but is updating the columns. So there are columns coming out, and I'm trying to keep the data set up to date. So there's a data set on the GitHub page, so that you load a data frame and you can then search it for which issue of the Grids and Datums column is up to date. And he then gives you quite a lot of anecdotal reference. So I knew about this one before, but it is described in his column. This stone block, as I can point here, this is the vertical datum. There's a small metal ball on a metal bar which sticks out, and it's the top of that ball, which we hope nobody has sanded off, which is the Norwegian datum. And there's a little metal plate, which if I'd zoomed in, then I think all of the color filling in the letters has been washed away. But that says the height above mean sea level in the harbour was changed after better surveying instruments became available in 1917 or something like that. But this block of stone, so that it has the 0 in altitude, and there's a similar depression in the middle of the top of the block, which is the prime meridian, which goes through the middle of the block. So the 0 line for longitude goes through the middle of the block, and the 0 so that this is the absolute beginning of the Norwegian mapping system, and it's just outside the window of the director of the mapping agency, as it was. Now the building is empty, and you can see the next thing that's going to happen is that this monument of surveying history is going to end up in the skip.
Oh, no.
But that was how you instantiated systems then. This was somewhat complicated because at the time Norway was under a the Swedish king was also king of Norway, but Norway was a semi-independent country, but Norway needed to establish where the border with Sweden was, so that the border with Sweden was the most important thing to survey. It's quite long. It goes all the way up the Scandinavian peninsula. So we've been through some of this already, but I'll try to explain the institutional context. Almost nobody now alive can remember in free and open source software can remember not using Proj. Proj by Bivand started in the 1970s, then came on as a C library, and there were no datums because at that stage the application area was North America, in particular the US. This was USGS, so that everybody used NAD27, so that there were never going to be any datum transformations. All you were going to be concerned with were coordinate conversions, so that the library was just dealing with coordinate conversions because everybody had NAD27. And when the library was initially written, this was simply the way it was done. And so that the release as a C library in 1985 reflected this. There was an unwritten assumption that what we're dealing with is NAD27. The same thing in the map Proj library written from Bell Labs and available in, as I'll come to in a moment, available in R. It was written by Don McIlroy, who piloted his own plane intercontinental. So he flew alone intercontinental when he was going to meetings, and he wrote his own software to do the navigation. And this also used the Clark 1866 ellipsoid. Done. So that was how Proj was originally written. But in the early 2000s, it was realized that, and this was Frank Warmerdam, he said, we have to kludge things to introduce a way of handling datum transformation. And the way that it was done was to say that WGS84 we know, so that we need to say for each coordinate reference system, geographic or projected, what is the relationship of the underlying geographic CRS to WGS84? As then, if you were moving from a NAD27 state plane to a NAD84 UTM, then you would go first to WGS84 and then out again. So that you'd be making two possibly datum transformations. While this was going on, oil was being found on continental shelves. So the oil was being found on continental shelves, but the datum and standard projected coordinate datum definitions and the standard projected coordinate reference systems for the coastal jurisdictions were very often different. So that if the politicians and the economists and the oil companies have agreed on a division on the median line, where is the median line when it's at home or when it's not at home? How do we divide up the tax revenue? How do we divide up the exploitation rights? And the oil companies established the European, because this was most pressing in the North Sea, the European Petroleum Survey Group, which is where the EPSG authority name comes from. And they're still going. So that trying to avoid conflicts over this oil's mine, no, it's mine. Was trying to establish shared standards so that many of the standards which we now see were actually initially established by the surveyors of oil companies who sat down together. So that I think Roger Lott at one stage was working for Shell. So that it was oil company surveyors sitting down together and saying, how can we make sense of this mess? And the sense they made, then they talked to other international geodeticists and So we've ended up with a series of different definitions, of which the most recent is ISO 19111, which is a definition of how to represent coordinate reference systems. It's not pretty, but it's where we are. The EPSG database is updated regularly, and it includes, in addition to the definitions of coordinate reference systems, it also includes tables of how to do transformations between datums. And these are then saying that some organizations have signed off on how to do this. Now, the representation using the well-known text 2 of 2019, so that the international standard representation, can be examined at different levels. The first ones I'm going to look at using Proj directly. So then you'll see how both Python and R sit directly on top of Proj for doing this. So that if we then look at the GeoJSON definition, which is the OGC, so the Open Geospatial Consortium Coordinate Reference System of 1984, which is a geographical coordinate reference system referring to the WGS 1984. So this is what Proj returns. There's a small utility program which comes with the Proj library. If you install the whole Proj library, then you get this one built on top of the library, and it tells you that the legacy Proj4 string, which would define this, would be to say that its Proj is longitude, latitude. The datum, there are 3 datum key values which are still valid. They are WGS84, which the Proj library still understands, NAD27 and NAD84. It still understands those datum values. However, the proper representation now, which, as you can say, takes a little more space, so that you get this as the Proj4, you get these two key value elements. No defs just meant legacy, don't use any default definitions, because the default definitions would kick in if you hadn't provided any. And type CRS is a new statement, which means that it's a coordinate reference system. But the WKT2 well-known text 2 2019 string then starts out by saying, okay, so this is a geographic coordinate reference system with a name, and then you get down here to its ID with the authority and the value. Within this, it says, okay, we should go directly to the datum, but what do we get if we have, this is in recent PSG database versions. It says, okay, sorry, WGS 1984 was almost 40 years ago, and we have other versions which have kicked in subsequently. So that these are the transit was the very first version, and then the other ones are in relation to different international terrestrial reference frames over time. So that these are then other definitions which are used, and the same epoch-based iterations, movements, also apply to GPS. So the GPS is not using the original WGS 84 from 1984, it's using one from some years ago. And then they roll over when a new one comes out, they wait a bit, and then they go for the new one. So that even recorded GPS positions from 15 years ago, if you still have the one which you took on your handheld, which used up the batteries in about an hour, then they will be taken in a different terrestrial reference frame. You get then okay, so the prime meridian's not a problem, and then you get to the axis order. The axis order is eastings are first and northings are second in GeoJSON. Now, what is going on here is that the access, so Projinfo is saying, okay, so here I want the definition of a coordinate reference system. What does it do? So let's look at the internals of this. What it's doing is connecting to the ProjDB SQLite database. So it goes in, these are all the tables. There are 43 tables. So there's quite a lot of tables, but the programming in Proj knows which tables to go to. So, okay, so we go to geodetic CRS. Then we want to select from geodetic CRS where its name is the one we could have seen above for the OGC CRS 84. Okay, so this is what we get, and then you get a coordinate system authority name, the coordinate system code, the datum authority name, the datum code, and these are then giving you a relational database that then gives you the code where it's going to look up the values, so that it's constructing the well-known text version by going out to the database and saying, well, okay, so this is the name we know, go here, pick up all the bits and put it together as something which looks a little bit like GML. So we can then go into the, from selecting from the geodatum table where the code is the one we could see here. So copying that. So that's all that's going on. So it's got a big-ish 6 mega, so it's not big, but and this database gets updated for each release of Proj. The database gets updated, and you can access the database from any SQLite reading thing. You don't want to necessarily do that because when Proj started using the database, the size of the Proj library grew from tiny and compiling in no time to big. So it's got much bigger, 10 times bigger. The number of code lines has really ballooned, but quite a lot of it is trying to optimize searching through the database tables. Now, one minor getcha is that if you go through Google GDAL rather than going directly to Proj, then it uses some other approaches. That in this particular case, because of an issue which was raised by people who needed the GeoJSON representation to not use the ensemble, then it comes out like this, so that it says, okay, so we've got a known datum rather than you've got a candy store ensemble. Choose. You have to choose datum, so that they and the things which are then dropped is that there's no usage block and no ID block for the representation, and it drops the ensemble representation, despite the fact that it's using the same database. So that when you're asking through Google, so that the Google command line utility, Google SRS info with the same named coordinate reference system, then you get a slightly different response, which we'll see also later on. Now, data transformation works in more or less the same way. The arguments for moving forward on this came in particular from Evers and Knudsen. They work for the Danish National Mapping Agency, and Denmark does agriculture. Right? It doesn't do very much heavy engineering, but it does agriculture, and precision agriculture matters. So that if you're going to look at, you probably realize that until this month, if you've got, what's the company called, John Deere Agricultural Equipment, they have closed source welded hood software for doing precision agriculture. So they have to provide the updates. In Denmark, they're more I was going to say anarchist, but they want to have insight into what's going on. So they were looking at ways of doing precision agriculture, which gave you more control over things. And then they realized, okay, so that Proj is out of date. so that we can't get the precision we need to optimally dose fertilizers or whatever on our fields. So, and the same thing in the Netherlands, the same thing in Germany, and anywhere with an interest in limiting pollution from runoff, where you're saying, okay, so the argument for precision agriculture, it may be bottom line, but it's also to do with reducing the costs of fertilizer applications, that you apply them where it's needed. You don't apply the same level of fertilizer over the whole field. So they said, okay, so that's construction engineering, that's precision agriculture, and we have from the satellites very precise position, but why can't we handle this properly? So the first thing that they dumped was transformation hubs. Now, in Proj 4, it had been introduced, early binding had been introduced as an easy way of settling things, that if you gave a definition of a coordinate reference system, it also, at the same time, defined how to get from that to the WGS84 data. So that if you're going from one definition to another definition, you immediately know how to get through the hub. But late binding uses, so how can I go directly from one to the other? So instead of doing two potentially lossy operations, you do one, reducing the error. So this is Martin Desruiso explained this on the project mailing list, that this is also coming from ISO 19111. Forget about any hubs. Don't do hubs. We have tables in the database saying how to get from A to C without going through B. And the way in which Evers and Knudsen did this was to say that what we need to do is to express transformation pipelines, so that which steps need to be taken in order to get from the source to the target coordinate reference system. So that Proj 5 introduced transformation pipelines. So the example here from Latin America is how fast the crust is moving. So the picture gives you sort of, okay, so we're talking about millimeters per year, so 20 millimeters per year. 10 years, 20 centimeters, 40 years since 1984. So that's about a meter for some places. In Peru, in places with more tectonic activity, there's more going on, so that the crustal movement is, it's not a big deal for the social sciences, but if you're a construction engineer, you're going to put your bridge slightly in the wrong place, which people managed to build bridges before, but then they had surveyors on site and they weren't using GPS to align things. So if we take the Chicago Board of Trade building as given by Wikipedia, which it turns out to be a really bad choice, because the examples that I've run before have usually used the John Snow pump, and moving across the sort of the barn raising for Proj, then you're off by about 120 meters. If you haven't chosen the correct way of doing things, you're saying, okay, this is, then you're a long way off. Here, we're in the 5 meter, 1 meter. You look at the numbers and you say, well, why does this matter? But it matters if you're in somewhere else in the world where the differences are more significant. So assuming that the coordinates given by Wikipedia for the Chicago Board of Trade building are written adequately adequate. And I'm also assuming that they're in NAD 83 HAN, which is the high accuracy reference network. So that's for North America. And we wish to compare this modern point with an old map, and the old map's in NAD 27. So we need to convert this point to NAD 27. So look at the description of the HAN. This is the full description of the HAN So there's no doubt about what this is. It gives a datum in the NAD83 high accuracy reference network, no ensembles, we've defined it exactly, so good. If we then want to go to NAD27, we could go to NAD27, again, a geographical CRS, and use the S3 104,000. And then this is the North American datum of 1927, the Clark 1866 ellipsoid. The Clark 1860 ellipsoid as defined by NAD27. There is another definition with the measures in feet, but using the meters. And scope not known, area not specified, the bounding boxes, so anything on the spheroid, and we can then search for candidate operations. So this is what you should already have grasped, is that what Proj is doing is it has a database with possible routes. So it's got definitions of coordinate reference systems, and for most of those coordinate reference systems, the database has a table. If you want to get from A to C, this is the way to do it. And so it goes into another table giving you the description of how to get there. And this can be queried in Proj. And this is then using the Proj utility Proj info by saying, in this case, we want the output to be represented as a Proj string because it's a lot shorter than the WKT2 2019, which it doesn't fit on the screen. And we're going to say we want a spatial test of intersects, so that the area of application and the point intersect. So and we're giving it a bounding box because otherwise we get between 50 and 100 candidates, but some of them apply to, because we've got a whole of North America and the whole of North America, so that some of them apply to different states, so that we want to give it a bounding box to say what's the local choice, so that we don't get too many choices, that using a bounding box or what's known as an area of interest is relevant. And then we've got the source geographical CRS, the target geographical CRS, and it's found. So what I'm doing here is unsetting Proj network, and I'll come back to this in a moment. And it's found one, which is obviously the one we would really want. It's got an accuracy of 0.2 meters, so that's good. And at least one grid is missing, so that it could use the specific high accuracy one for Illinois, or it could use CONUS, which would be the one which was used traditionally. So these would be the grids that it would need to make a grid transformation, because those grids are showing how the transformation relationship is warped. But we can't do that. We can't even use the one for Michigan because the grids are also missing. So the one we can do is simply move from the one ellipsoid to the other, because we know that one is the Clark 1866, and we can move to the WGS 84. So we can move between those. So we won't get the same number out, but we get a slightly different number out, but it'll be the one where we don't know how accurate it is. In the John Snow pump case, if you're saying, okay, we'll go with ballpark, then you've got almost 120 meters difference. So we can try and make the datum transformation for the point, and we get out a point which it differs. This is 806, this is 803, and here I've got northings, eastings. This is 222, 218, so 4 meters and 3 meters. So, and that's coming from the ellipsoid. So that's just. So, but what are these grids? And the grids are then an open access question that many mapping agencies have not been, until now, they've been military secrets, so that you can't make them available. And it's only recently that people have realized that any potential enemy probably has better data on your grids than you do, because they're observing you from above. So they can guess how to fit things in, or that they're using satellite imagery and position imagery, which are using the same terrestrial reference framework. So they don't have a problem of old maps. So what we could do is turn on the Proj network. There's a link here showing where it is. So if you want to visit that, you can see it. And that then lists the grids which are available in the area that you're interested in. So you start with the whole world and you've got to zoom in, but you can pick up on the fly the grids if you turn the network on. So if the network is turned on, we can grab the grid which is needed on the fly, and it's then cached locally on your machine and can be reused unless a subsequent use reveals that a newer version has become available. So that in general, it will put it somewhere in your on Windows.local on Mac, then it will be the same. So that it will be somewhere in the user data areas. I've been putting it here in an R temporary directory just to be sure that it was empty, because otherwise I'd be trying to run the example using a cached version of the grids. We don't get much change. We got a 1 meter change in one direction, a 1 meter change in the other direction, compared to not doing it in that way. And then we'll unset the. And what's going on is that it's downloading. Previously, we had nothing in the temporary directory. This is here. And here then we can see that a CacheDB has been established, another SQLite database, and within it then we can see what has been downloaded. So it's this particular file which has been downloaded and used in making the change. It's if we in this case I've downloaded locally the CONUS. These are then cloud optimized GeoTIFFs. The Proj content download network is hosted by Amazon. And this is what the CONUS looks like. So actually, where we are in Chicago, there's very little offset in either way for the CONUS. If we'd done the same for the Illinois, then you'd also see that the differences were in centimeters between the HAN WGS 84 and then 27. So actually, this is one of the worst places probably in the world to try and demonstrate the impact. We've now got 5 minutes to go, and the rest of the talk is about the R implementation and the Python implementation, but both of those just sit on top of Proj. So that's why I've taken the necessary time to show you where all of this is coming from the underlying library. And for those of you who like playing with stuff, then that's where you should go. The exercises which I've added in for people who enjoy that kind of thing are to try to determine what the declared coordinate reference systems are of data provided in the SP data package. As I just noticed preparing this workshop that actually we don't mention that on the help pages, and we should have done. Again, years ago when the data sets were first made available, then what really mattered was making the data available. It didn't really matter that we provided a verifiable coordinate reference system, but the world has now moved on, so we now need to revisit that. And the same thing if someone wanted to look at the Geodar data directory and see what is available there, then you could also look through those. And the difficult bit is essentially trying to work out whether if you're flying on a plane in flight mode, you know you don't have the content download network turned on. If you're using, are there any Windows users here? Okay, so that on Windows, it's possible to get access to some things through what's known as OS Geo4W, and they package all of the grids when you download, so that the actual OS Geo for Windows was about 100 mega, and now they add in the 600 mega for all of the grids, and that number is growing. So each time a new release comes, then it's grown by another 50 mega or so, because we're trying to encourage jurisdictions to make their grids available open access. And so there's a question in R and in Python. The decision is essentially not to download, but to use the content download network. But it then means that users have to be aware that maybe you have to turn on the content download network. So that the trick, both in Python and in R, is to use the environment variable. So if you know that you're going to be using the content download network, then you can do it that way, or in the directory which is not user writable, where the ProjDB database lives, there's a file called proj.ini, where you can also edit that file and make it turn on the content download network. But you then get stuck if you're on a plane and on flight mode, and you have to remember to tell it to turn it off before. I tend to use the environment variable, because then I have control from workflow to workflow. And both in SF, not in Terra, in SF and in PyProj, again, GeoPanda sits on top of PyProj, but it doesn't give you the detailed access that you get in PyProj to turning on and off the content download network. It's the same a little bit in Terra. Terra is sitting on top of Google and Proj. It goes through Google, but you haven't got a handle to turn on the content download network, so you use the environment variable for doing that. And for those of you who read through the rest of the presentation, because my presentations are like this, we could go on till halfway through the afternoon. But it's fascinating stuff. It's one of the anecdotes to round off from grids and datums is the ability that a field anthropologist would envy of Cliff Mounier talking to retired people from mapping agencies about whether they remember how things were done in the old days, because quite often, quite a lot of the technical twists, somewhere at the back of my head, I have an anecdote about the precise details of the datum for the Faroe Islands being refound on a slip of paper written in pencil behind a filing cabinet. But I'm not sure whether I didn't dream that. But that's the sort of the anthropological detail that you get from looking at Cliff Mounier's things. Coordinate reference systems are also made by people, and some of the people had particular grasped views on things, and actually we owe a big debt of gratitude to Cliff Mounier for digging up the old things, because very often we need to compare old and hard to resolve coordinate reference systems with newer ones. So I'll conclude there, and we've got another minute.
Really briefly, anybody has a remaining question online or in
particularly
person?
Online, because the people who are on site can grab me.
Yeah. Okay, anybody online has a question? I think we're good. I had encouraged them to ask questions throughout, and there weren't any. So excellent. Then a round of applause for Roger. Thank you very much for taking the time. Thank you for everyone online for joining us as well. And we will see this presentation online on our YouTube channel as well with a link. Take care, everyone.